So let's look at another exercise. So this exercise is from the book, page 100. So if f of x is a piecewise function, it is equal to square root of x minus 4 if x is greater than 4, and it is equal to 8 minus 2x if x is less than 4. So we are asked to determine whether the limit of f of x as x approaches 4 exists. So, a small reminder, a limit exists. So the limit of f of x as x approaches 4 would exist if the left-hand side limit, so the limit of f of x as x approaches 4 from the left, is equal to the right-hand side limit. So let's check if this is true in our exercise. So let's start with the left-hand side limit. For the left-hand side limit, we look at when x is less than 4. So we take the function 8 minus 2x. And in such a case, as I said earlier, it never hurts to plug in. So let's try to plug in. We get 8 minus 2 times 4, which is 0. And we get a real number, so this is our answer. Now let's try the right-hand sided limit. For the right-hand sided limit, we look at when x is greater than 4, so we look at square root of x minus 4 as x approaches 4 from the right. So again, let's try to plug in. We get square root of 4 minus 4, which is equal to square root of 0, which is equal to 0. So this limit is equal to 0. And we can notice that the limit of f of x as x approaches 4 from the left equals to the limit of f of x as x approaches 4 from the right, and both are equal to 0. So the limit exists. So the limit of f of x as x approaches 4 exists and is equal to 0. So now we will move on to another technique that can help us to solve limits, which is to rationalize. So as I mentioned before, it's always good to simplify limits. So as always, let's first try by plugging in, and then we will continue by doing this technique. So if we plug in, we get 2 plus 1, the square root of that, minus square root of 4 minus 1, divided by 1 minus 1, which gives us square root of 3 minus square root of 3 over 0, which is 0 over 0. So again, whenever we get 0 over 0, always simplify. And the way to simplify, so I will erase this to have some space. This gives 0 over 0, I will write it here. So the way to simplify is to rationalize whenever we see that we have many radicals. And if you're having a lot of trouble with rationalization, don't forget that we have another video to help with this. So, how can we rationalize the numerator? You might notice that this is square root of a minus square root of b. So if we multiply it by square root of a plus square root of b, this will give us a minus b. Basically, we multiply it by square root of 2 plus x squared plus square root of 4x minus x squared. And again, we always have to multiply the numerator and the denominator by the same factor. So this becomes limit as x approaches 1. The numerator becomes a minus b, so it becomes 2 plus x squared minus b, which is 4x minus x squared, and the denominator becomes x squared minus 1 times this factor. So let's continue simplifying in the numerator. Let's distribute the negative. So 2 plus x squared minus 4x plus x squared. And in the denominator, we have x squared minus 1. A reminder that a squared minus b squared simplifies to a minus b, a plus b. So x squared minus 1, which we can also write as x squared minus 1 squared, simplifies to x minus 1 times x plus 1 times square root of 2 plus x squared plus the square root of 4x minus x squared. So we have some like terms in the numerator. We have an x squared here and an x squared here. So we can write this as 2x squared minus 4x plus 2 divided by the denominator. We keep it the same. So what we can do after that is that we can factor the numerator. This is a quadratic. So this factors to 2 times x minus 1 all squared divided by x minus 1 times x plus 1 times square root of 2 plus x squared plus square root of 4x minus x squared. And again, if you're having trouble with factoring, look at our previous videos. So then we will simplify. We have an x minus 1 in the numerator and an x minus 1 in the denominator. So this becomes limit of 2 times x minus 1 divided by x plus 1 times square root of 2 plus x squared plus square root of 4x minus x squared. And anytime you cancel something in a fraction or you simplify, anytime you can always try plugging in again. So in such a case, let us try plugging in. So we notice that if we plug in, we would get 2 times 1 minus 1, which is 0, divided by 1 plus 1, which is 2, times the square root of 2 plus 1, so square root of 3, plus 4 minus 1 plus square root of 3, which is 0. Because it doesn't matter what is in the denominator if it's a number, as long as it is not 0 or infinity. So 0 divided by a constant is 0. So the answer of our limit is 0. So this is just a summary. You can always start by direct substitution. It can always help, and if a is in the domain of the function, it will work and give you a real number. If you have something, if you plug in and you get something like 0 over 0, always try to simplify. To simplify, there are several methods, and we looked at a few today, which are factoring, especially if you have polynomials, rationalizing, especially if you have radicals, and often combining, as in simplifying fractions, finding a common denominator. So now let's look at the squeeze theorem. Squeeze theorem, as the name suggests, we are squeezing something, and some people call it the sandwich theorem. So the squeeze theorem, if f of x is less than or equal to g of x, which is less than or equal to h of x, when x is near a except possibly at a, and the limit of f of x as x approaches a is equal to the limit of h of x as x approaches a equals to L, then the limit of g of x as x approaches a is also equal to L. In case you did not understand this, let's look at this graph to better understand it. As you might notice, this is H in green, this is F in blue, and G is in between in red. And you might notice that H, for most of the time, it's bigger than G. And F, for most of the time, it's smaller than G. And G is in between F and H. Now, if the limit of h of x as x approaches a, which is here, this point, is equal to L, and the limit of f of x as x approaches a is also equal to L, since g is between f and h, we can say that the limit of g of x as x approaches a is also equal to L. So let's look at an example to help us. Let's say we would like to find the limit of x squared sine 1 over x as x approaches 0. One thing you might have learned from previous videos that the sine function is always between -1 and 1. This is its range. So we would like this function in between to look more like this one. We want it to be x squared sine 1 over x. So what we do is we multiply everything by x squared. And now that they look the same, we can take the limit as x approaches 0 of each of these. And notice here how I took the negative outside the limit because negative is a constant. It's as if saying -1 times x squared. So let's start with the one on the left. The limit as x approaches 0 of x squared is 0, and even if I multiply it by -1, it will still be 0. So I keep the middle the same. And on the right, the limit of x squared as x approaches 0. If I plug in 0, this will also give us 0. So since the limits from the upper bound means this side on the right, and the lower bound, which is on the left, are equal, then by the squeeze theorem, always mention the name of the theorem, the limit of x squared sine 1 over x as x approaches 0 is 0. Now we will use the squeeze theorem in order to prove that the limit of sine x over x as x approaches 0 is 1. So we have this figure in front of us. Basically what is happening is we have this circle, we have x an angle, x is between 0 and pi over 2, because we have, if x was 0 it would be here and pi over 2 would be up here, so x is in between. And then I took 2 points on the arc to be D and B. So if I draw perpendicular lines to the x-axis from B up to when it intersects with this line here, I name the point C, and same for A, I draw a perpendicular line up, and then I name this point of intersection D, and then I drew a line between D and B. So one thing we might notice is that we have a triangle DOB. I will highlight it. This is our triangle DOB. I highlighted it in yellow. And then we have a triangle COB. Also, we have the arc DOB. Maybe I should use a different color. I know maybe the figure is a bit messed up, but if you can notice now that the area of the triangle DOB is less than or equal to the area of the arc DOB, which is less than the area of the triangle COB. I will zoom in into the figure because as you can see, this yellow part is smaller or equal to the red part, which is smaller or equal to the green part. Now I will erase this just to make the figure clearer. So this is a good step for the squeeze theorem, because as you know in the squeeze theorem we also always start by making an inequality. So now let's find each of these areas. So let's start with the area of the triangle DOB, which I will highlight. This is the triangle DOB. So as you know, the area of a triangle is half of the base times the height. Now the base of the triangle, first I will write it's the base times the height divided by 2. Now the base of the triangle OB is the radius, because B is on the circle and O is the center. And this we will suppose is a unit circle, so the radius is 1. So the base is 1. So now the area is 1 times height over 2, or we can say just height over 2. Now what is the height? The height, if we look closer to this triangle, the height I will highlight in yellow is this dA. How can we find dA? We can note that sine of x is equal to opposite over hypotenuse. In this case, the opposite in the triangle ODA, the opposite is dA over 1, because the hypotenuse is OD and OD is the radius. And when I write this bar above, I'm talking about length. So sine x is equal to dA. Now this is our height, so our height equals to sine x. So now the area of the triangle DOB is equal to sine x divided by 2. Let's use a different color now for the area of the arc DOB. So I will do this down here. The area of an arc, the formula is half r squared theta. R is the radius, and theta is the angle of the sector in radians. So we know that the radius is 1, so we can rewrite this as half of theta. And in our example, we defined theta, the angle, as x, so we can rewrite this as x over 2. Finally, we will work with the area of COB down here. The area of the triangle COB, as we already said, the area is the base times the height divided by 2. So it's base times height divided by 2. Let's look at the triangle. So triangle COB, as you might notice, the base is OB, which is the radius, so it is 1. So we can write the area as height divided by 2. Now let's look at the height. The height is CB. So how can we find the height CB? We can again use trigonometry. So tan of x equals to opposite over adjacent. So it's equal to CB divided by OB. And OB is a radius, so it is 1. So the tan of x equals to CB. Now we can plug this back in here. So the area is height over 2, which is equal to tan of x over 2. And now, with all of that in mind, we can rewrite the inequality. The inequality becomes sine of x over 2 is less than or equal to x over 2, which is less than or equal to tan of x over 2. One thing again to keep in mind is that x is between 0 and pi over 2. So x is approaching 0 from the right. And another thing to keep in mind that x is never touching 0. We are always approaching 0. So now, because of that, let's continue with our inequality. Again, as we got sine of x divided by 2 is less than or equal to x over 2, which is less than or equal to tan x over 2. So it doesn't hurt to get rid of all the 2's, to multiply everything by 2. This gives us sine of x is less than or equal to x, which is less than or equal to tan of x. And now we want this to look more like this function up here. So one thing we can do is we can divide everything by sine over sine of x. So sine of x, we divide everything by sine of x on all sides. So this gives us 1 is less than or equal to x over sine of x, which is less than or equal to. Here, tan of x is sine of x divided by cos of x. If we divide this by sine of x, we get 1 over cos x. Again, this is not exactly the function we want. The function we want is sine x over x. So we want to flip, we want to take the reciprocals of everything. And just to keep in mind that if we take the reciprocals, all of the inequality gets switched. So we can take cos x to the other side. So basically, we get cos x is less than or equal to sine of x divided by x, which is less than or equal to 1. Now that we got this function, let's take the limits. Limit as x approaches 0 of cos x is less than or equal to limit as x approaches 0 of sine x over x, which is less than or equal to limit as x approaches 0 of 1. And as I mentioned before, that x is between 0 and pi over 2. So if it is to approach 0, it will approach it from the right. Therefore, we might as well put these little positive signs to indicate that we are approaching 0 from the right. Now, as we approach 0 from the right, the limit of cos of x as x approaches 0 from the right is 1. If you want, you can draw a graph of cos of x, which looks like this. So as we approach 0 from the right, we are approaching 1. This is less than or equal to limit of sine of x divided by x as x approaches 0 from the right, which is less than or equal to 1 because the limit of a constant is the constant itself. So, by the squeeze theorem, the limit of sine of x divided by x as x approaches 0 from the right is 1. So this is how we prove that the limit as we approach 0 from the right is 1. A similar argument is used to prove as x approaches 0 from the left, because one thing to note is that cos of negative x is equal to cos of x, so we will get the same answer even if we're working from the left. But you can always, because of that, you can always conclude that the limit of sine of x divided by x as x approaches 0 is 1. Again, it is always very important to check with your professors whether you need to know how to prove also from going from the left as x approaches 0 from the left, or whether this is enough. And always check to know how much work you are supposed to show.